All right, so here we go with lesson number 15. In this lesson, we tackle negative exponents, scientific notation, and roots. We'll start with our demo. Let's look at the pattern after filling in the right-hand column to discover why any number raised to the 0 is 1 and what is meant by negative exponents. So last class we saw this, right? That any number raised to the 0 is 1. So I asked you to just take my word for it then, but now we'll explain why it's perfectly reasonable to define any number to the 0 to be 1. Okay, let's fill in here. 3 to the 4th power is 81, yeah? So we're just going to fill in these blanks in this column. 3 to the 3rd is 27. 3 squared is 9. 3 to the 1st is 3. Okay, let's pause right there. So those are 4 facts we're all comfortable with. But if we continue the pattern down the left-hand side, 3 to the 4, 3 to the 3rd, 3 to the 2, 3 to the 1, the very next thing in this pattern, this list, is going to be 3 to the 0, yeah? Okay. And let's look for a pattern here. What can you do with 81 to turn it into 27, where the same thing will turn 27 into 9, and the same thing will turn 9 into 3? Divided by 3, yeah? If you just take the number and divide by 3, that gives you the number that's in the next row. So if we buy that, so let's see, so 9 divided by 3 is the 3, and 27 divided by 9 is, 9 divided by 3 is 3, 27 divided by 3 is 9. So if we buy this idea of, hey, just keep dividing by 3 as you go down the list, then the next number in the list should be this purple 3 divided by another green 3, which is 1. So it's just a continuation of the pattern, right? We're used to exponents building up, but if we just go backwards, it's the same idea. Instead of repeatedly multiplying by 3 in this case, we're repeatedly dividing by 3. Well, that was so much fun. Why don't we just continue right past the number 0 and hit some of these negative integers? So the next one after 3 to the 0 is 3 to the negative 1. And if we buy this pattern of keep dividing by 3, then what fraction is our definition here? Is 1/3, right? Just take the previous number, which is a 1, and divide it by 3. What about the denominators? Yeah, we are, because dividing by 3. So this next one, we're going to take the 1/3 and divide it by another 3. And that's 1/3 times another 1/3. So yeah, we're just going to end up multiplying denominators here. So the next guy here, if we take 1/3 and divide it by another 3, do we see it's 1/9? So 1/9 goes there. And the next one is 1/27. And then the last one, 1/81. So go ahead and fill those guys in if you haven't yet. And then we'll make this last observation here. 81 by itself, not 1/81, but just plain 81 is in this list already. 81 is also the same as 3 to the 4th. So this is really 1/3 to the 4. And by that? So what that means is that 3 to the negative 4 is the same as 1/3 to the positive 4. And that's our definition of negative exponents. If you see a negative exponent, you put a 1 on top of it, and you make the exponent positive. That's it. And this is why that's a good definition for a negative exponent. It's just following this pattern. So here it is. X to the negative n. I see a negative exponent. I just plop a 1 on top of it, and I make the exponent positive. 1/x to the positive n. Okay? Our definition for negative exponents. Takes a little bit more work to see it, but it turns out that if you have a negative exponent in the denominator, then you can make it positive and move it to the numerator. As an example, 1/3 to the negative 2 becomes 3 to the 2 upstairs in the numerator, and that's just 9. That one's not as easy to see. Okay, so let's see if we can apply this idea. First, a quick shortcut, and then we'll do our example. So number 2, here's a shortcut for negative exponents. Negative exponents indicate movement. If you see a negative exponent in a numerator, make the exponent positive by moving the term into the denominator. So negative upstairs becomes positive downstairs. We're just talking exponents. And if you see a negative exponent in a denominator, make the exponent positive by moving the term into the numerator. So you see a negative exponent, you move it to where it's not. If it was upstairs, you move it downstairs. If it was downstairs, you move it upstairs. So let's try this example here in number 3. So the first thing we'll do, we'll write this out even though the answers are kind of there, so try not to peek. So first thing I see here is this d cubed to the negative 2. How do the exponents multiply those guys? Yeah. So I'm going to copy everything else. Get that? Okay, and if you've never seen negative exponents before, that could be frightening, but really the only thing to know about negative exponents is that you move them and make them positive. And so our next line, I see 5, I see r to the negative 9. That r to the negative 9 is currently in the top. I'm going to move it to the bottom and make it what? R to the 9. So big old fraction, r to the 9 is right down there. That r to the negative 9 moves and becomes positive 9. It will. I'm going to do that in 2 steps, though. You're right, though. One common mistake is to take the 5 and move it as well, but that 5 has nothing to do with that exponent negative 9, right? Negative exponents are really weak. They don't reach as far as some people think they might. So the 5 has no reason to go anywhere. It's just hanging out. Likewise, that 25 in the denominator, does it move or stay? Stays. Just copy it down. Next thing I see is r to the negative 5th. I see a negative exponent. I move it and I make it positive. So this used to be in the bottom. It moves to the top and becomes r to the 5th. Next thing I see is d to the negative 7. Move or stay? Move. So it goes upstairs and becomes d to the 7. Last thing is d to the negative 6. Move up d to the 7. D to the 6. Thank you. Okay, so let's clean this up a little bit here. 5 and 25 reduce and just leaves a 5 down there. Let's handle the d's first. What do you do with those powers when they look like that? Add those together, so we get d to the 13. Okay, and then finally the r's. I have r to the 5th and I have r to the 9th. Now if you just subtract them, 5 minus 9, you get negative 4, which is okay, but it's negative. And one of our new rules from today is going to be you don't get to leave any negative exponents in any final answer. So why don't we make our lives easier? And instead of just saying always subtract the top number minus the bottom number, in this case 5 minus 9, why don't we just do big minus small and then put it wherever there are more, wherever the big is. So I see there's more r's in the bottom. When I cancel them, there are definitely going to be r's left over in the bottom. How many? 4 of them. So this is our answer here with the 5 in the front. D to the 13 over 5r to the 4. Okay, so real common mistake people make, if I give you something like 2 to the negative 3rd power, just about guarantee that at least one person is going to do this on the next quest and say, oh, that's the same as negative 2 cubed. Negative exponents have nothing to do with negative numbers. It doesn't make the whole thing negative. It's completely independent of negative numbers. So 2 to the negative 3 really means 1 over 2 to the positive 3, right? That 2 to the negative 3 you could think of as being up on top. It moves to the bottom and becomes 2 to the positive 3. So this is 1/8. Matt?
You put it down. Like, it worked.
Mm-hmm.
It worked for me.
Is that all there was to it?
Yeah. But then I forget what it was to go from like the negative up to the top. I forget what it was, but I know that looks like a crying baby, so you put it down.
Just raise your hand if you've seen the baby explaining the negative exponents. 3 people, and the rest of us are looking at you guys like you're crazy.
I probably sound crazy right now, but that's how I know to put it over a fraction.
I never really understood that.
Okay. here's the idea. Here's the idea. You can think of a negative exponent like a baby, and if a baby is crying, they're negative, so negative exponent is a crying baby. And if they are negative, they want something different. And so let's look at this r to the negative 9. That is a baby up in your arms. That r to the negative 5 is a baby on the floor. They are both negative. They are both unhappy. They want something different. So the baby in your arms, where do they want to go to become happy? They want to go down to the floor, so down to the floor, and now they're happy, they're positive. And the baby that's on the floor, what do they want? They want picked up. And so we put them upstairs, and all of a sudden they become happy. Yep. All right. Next page. Scientific notation allows us to easily work with very large numbers or very small numbers. We write numbers in this format by writing a number between 1 and 10 multiplied by a power of 10. This is also an 095 topic you might have seen. So here we go. On a particular date, the national debt was approximately that massive number. We want to rewrite this thing using scientific notation. Let's just make sure we can read this number out loud. This group right here is the hundreds. What's the name of the next group? Thousands. So I'm not going to write it all out. The next one. Millions is next. Billions is next. Trillions. So that is $15,460,000,000,000. And we want to rewrite that using scientific notation because, to be honest, that number is kind of hard to read, as we just saw, right? We had to literally count out the names of these places to figure out what it really represented. And it's also kind of annoying to write if you have to write all that and be careful counting all the zeros. So enter scientific notation to the rescue. So here's the idea. We need to rewrite that so that that number is something between 1 and 10 multiplied by a power of 10. Currently, the decimal place is here, and currently the number is 15 trillion and change. If I decided to say move the decimal point arbitrarily to there, just read that number. What is it? 15.46. Yes? Okay. Is that a number that is between 1 and 10? No, it's not. So the goal, you've got to get it to be something between 1 and 10. And there's only one way to do that for any given number. Where should I put the decimal place in this case? We buy that? 1.5. That is the only place I can put the decimal to get a number between 1 and 10. So that is what I have to do. It is part of the definition of scientific notation. So I'm going to write that number, 1.546. And we know that we don't need to write trailing zeros now because they don't affect anything given where the decimal point is. But 1.546 is definitely not the same as 15 trillion. So we have to pay for it by multiplying by 10 to the right power. And so the right power is always going to be however many places you moved that decimal point. So from where it was at the beginning to make it a 1.5, how many places did we move over? I heard one vote for 13. Is that right? 13 places over. And that's it. That's our answer. 1.546 times 10 to the 13. Scientific notation. Questions on that one? If we had instead decided to put the decimal place here, then it would be 15.46, yes? Times 10 to the, how many places does the decimal point go from blue to green? Is 12. That still represents $15.46 trillion. It is correct, it's just not what? It's not scientific notation, that's all. There are many ways to write 15 trillion. There's one way to write it in what we call scientific notation, and that's the 1.546 times 10 to the 13. So we'll just make a note here. Correct, but not scientific notation. Okay, so part B, the diameter of a typical bacterium is about 0.000000241 meters, pretty small. We write this number using scientific notation. Same idea as before. Decimal point is currently here. There's only one spot. Don't say it out loud. I want everybody to have a chance. I want you to put a new decimal point in that number so that you have something that's between 1 and 10. There's a lot of zeros. There's a 2, a 4, and a 1. Put the decimal place wherever it's appropriate to make a number between 1 and 10. Somebody we haven't heard from today. Where do we put it? Between the 2 and the 4. Because all those zeros are then irrelevant, and that is just the number 2.41, which is the only way to write a number between 1 and 10. So that is absolutely the right spot to put it. So we can immediately begin our scientific notation answer. It's 2.41 times 10 to the, how many places did it go? So it went 7. Is that Jillian or Catherine? Jillian says -7. What do you guys think? Yeah, I mean, like, there's something fundamentally different about what we did, right? Like in the first example, the decimal place went that way, and here the decimal place went that. There's got to be some way to tell the reader, hey, we went that way or the other way, right? They have to make a distinction. And yeah, the distinction is to call this guy -7. So really common mistake to make is people not quite knowing, okay, which one is the positive exponent on the 10 and which one is the negative exponent on the 10. I'll tell you that at some point back when I was in school, I memorized that when you move the decimal place to the left, it's a positive exponent. When you move it to the right, it's negative. But honestly, that is not a very memorable thing to know. I will say that I know that 10 to the 13 is a massive number. You guys know that too, right? Okay, so if you start with something massive, you got to end with something massive. Like, it doesn't make sense to say 15 trillion and then give me 10 to the -13. That's not right. It's got to be something big. And so big just means positive exponent. But this 0.000000241 is a teeny, teeny, tiny number very close to 0. And you know what? So is 10 to the -7, because 10 to the -7 from what we saw earlier today is really 1 over 10 to the 7, right? And that's really 1 over 1, 2, 3, 4, 5, 6, 7. That's really 1 over 10 million, which is quite close to 0. So if you start with a number close to 0, you better end with a number close to 0, something negative. So this is all that I'd encourage you to remember. If you start with a big number, you better have a positive exponent. If you start with a number that's close to 0, you're going to end up with a negative exponent. And if you do just a few of these, you'll start to get the pattern yourself, but not a bad thing to write on the reference sheet as you're preparing for the quest. Again, this is not going to be on the test. Questions on that? Okay, so there are 3 separate activities below. You're going to have to motor for the rest of class in order to get through them. Why don't we just stand up and stretch real quick and then jump in to the activities.